Decide immediately. Decide immediately.
What I want to present today is a bit on the technology, but very little and more on the benefits that we can generate from this kind of data. I said already that a lot of satellites are circling the Earth, and when we talk about satellites in Europe, so one of Europe's flagship projects is Copernicus, Earth observation component. And with Copernicus, we have the Sentinel satellites. There are Sentinel-1, which is a SAR satellite system, and Sentinel-2, which are optical satellites. And with this, so Sentinel-1, there are 2 satellites, and Sentinel-2, there are also 2, and each of them have the capability to map every point on Earth every 5 days. So and then there are, of course, other satellites, like there is the Planet system, which can virtually use it every day. And the specialty of the Sentinels is that they are free and openly available. So everyone can use this kind of data. Every 5 days, one image for SAR and one image for optical. When we are talking about SAR, it's all weather capability, so we can also see through clouds, so to say. But there are limitations also. So what I want to say is that there are different sensors which can be used in an integrative way to make an additional benefit. And we have a constant stream of data. We have already heard a lot about big data, and I think this is one common point here. So what we also see is a paradigm shift. So in the past, there was someone was taking one image. It was very costly, and then they were taking the image in the lab and they were analyzing it. Nowadays, we have, as I said, a time series available free of charge. So we are bringing not only now we are reversing it. So we are not bringing the image to the software, but we are now bringing the software to the image repository, because we don't want to duplicate all the imagery that is available, because it's a lot of data. So there are some technological issues entailed, and I just want to mention them. Many of them have already been touched upon in the last talks. Big data was Herwig already mentioned, which needs also proper data mining, data handling strategies. Cloud processing was mentioned several times. One thing which might not have been, because it's more technological, it's that modern software needs Docker container functionalities. So that means that you can bring your software to any repository, so that you are not fixed to one repository, but you can go to any data infrastructure system and process there. High-performance computing centers, you all know that. And also, we have also already seen that with this animal application, these on-demand systems through online services. So the customer doesn't want to pay for one service, but only on demand. Maybe I want something now, and I want it directly. But without further going into this technology, I want to show some of the benefit areas which we have been working on over the past years. One is humid tropical forest monitoring. You have already all heard in the last month about the rainforest burning in Brazil and stuff like that. Then also some land use classification applications, and also some near real-time change detection. Near real-time was also mentioned that we need the data more close to real-time and not so much in delay. So first of all, humid tropical forest, I don't think I have to explain why it is important and stuff like that. So just some things that in the humid tropical, it's relatively easy in this way, in terms of technological, because it is evergreen forest. So in terms of data processing, it's not as complicated as temperate forest, where you have a phenology. But what the problem we face, it's a lot of cloud coverage. And there are some areas where we have, even if we have every 5 days an image, we have sometimes cloud-induced data gaps, especially in mountainous areas. And when we look at SAR data, this is an example where you can see in Gabon, just for explanation, these dark areas here, they are non-forest, and these grayish areas, they are typically forest. And you can see, I will start the animation again, you can see on the back, on the front here, let's start it again, how the time moves. So you can see how this forest area is cut down for an oil palm plantation. And it's really huge areas. You can see the scale bar here. And this is in an area where you usually, during this time, you get maybe one image snapshot in optical data. So that's why the SAR data is so really interesting and important for the tropical areas. So this is SAR only, but if we want to combine them, this is just a recent work we have done for Peru, where we integrated the optical data and the SAR data. And what I want to point out here is, maybe you see the colors, that these yellow colors here, they are the areas of deforestation which have been mapped by both sensors. So that means there's not so much area captured in both sensors, and that's what I wanted to say with the different properties before. So the different sensors can map different areas, and we have a good complementarity between the results. So when we use all the data we have at hand, we get better results. This is the same what I wanted to say, just in different numbers. When we do the accuracy assessment, for example, the producer accuracy is almost doubled when we use both of these sensor types in the time series. When we're talking about land use classification, also here we have seen a paradigm shift from the classical signature analysis, where we had some bands for one image, and we see where cropland is located, and we classify that. Today, there are random forest machine learning tools, because we have such a huge amount of data. We cannot do a signature analysis like that anymore. So this is the movement. And this is just some figures again, where we see when we move from a monotemporal from one image to a multitemporal from one sensor, and if we include another sensor like the SAR sensor, we even get better results. Another example is this is a current Horizon 2020 project we're working in, where we are looking into this energy system, and we want to avoid this food versus fuel problem. So the idea in this project is to identify underutilized lands, which can then be used for biofuel production, so that we don't take any areas away from the food market, but only use those which are at the moment, because they are marginal, because they are not maybe not so good soils, or maybe because of political or social issues are not used. And our part is to try to identify these through the time series. And this is an example where we see that some areas where you can see in the time series these mowing events, and in others we cannot see them, so this is potentially underutilized. A similar thing where we also use this time series is for grassland classification. Of course, here, when you saw the previous slide and this one, so an extensive grassland can easily be mixed with an underutilized land, because if there are a few sheep on this patch of land, we cannot distinguish that, of course. But at least from the very intensive use, we can differentiate. The next part is the near real-time change detection. Why is this important? On the one hand, it's important to fight against illegal logging, for example, or it is, when we are talking about Europe, it's also important for when we have storms or insect infestations, and especially when there is a wind throw of the forest, then the authorities need to know quite fast how much is affected, how much budget they have to set aside for compensation, or also the sawmills need to know how much wood they can expect from these areas. what's the problem here? I said before that the humid tropical forests are very easy. This is dry tropical forest, and you can see here an animation over the year, and this is in Malawi. And here the colors are always the same for the same values. So it's not a change, not just a change in color, it respects the value. So that means that this forest here, it loses leaves, it gets totally leafless, and even they do, when you see here now these purple colors, they even do burning underneath the forest canopy. So it really looks, if you would only look at two images, it would look like a total deforestation. But the next time the rain comes in, the leaves green up again, and it's green again. So this is what we have to model. So this is what makes more difficult, and not that it's difficult enough. It means also that there is a gradient in terms of phenology. So not only that there is a gradient, it's not there is a phenology, but it's different for different land cover, and also different for in terms of area. For example, here in Malawi, in the east, you still get a lot of rain, while towards the west it gets more and more dry. So that's why you have here in the west, you have the gradient is very strong, while in the east it's more flat. And when we model this, we still need to account for changes in the seasonality. So that means when we would just have one model and say, okay, this is the typical curve, and in the beginning of November, the rain sets in, and then the values go up again. The problem is that sometimes the rain sets in the beginning of December. So we would detect a lot of changes during this month, which are not real changes, they are just a shift in the phenology. So that's why we use not only what I said before, this is this green line here, this is the general model, which we learn from the 2 or 3 years of data. We learn a general model, and then we have an additional filter, which is the Kalman filter, which adapts to slight differences in the individual year, for example. And then we get some outliers here, for example, the orange points, but only if these outliers are confirmed with the next observation, then we say there are really changes. And this is an example now for this Malawi area, and we see that in 2018 here there are the fully automatically generated polygons of change, and yeah, it looks very promising, I would say. The validation is at the moment still ongoing. We use the same thing also for European forest. This is an example for storm damage in Styria, and here is one result from in the yellow is a delineation from visual interpretation, but not from the satellite data, but from a dedicated airborne campaign, and the red one are the automatically generated. But this is now an online tool where you can put in the time, and we did it for one granule in Styria, and you can put in the time for which you want to have the changes, and then it calculates you the changes, and then you can download it and view it on the map. Another change area is bark beetle damage, which we have a lot of problems. Also, I heard in Czech Republic there's a lot of problems with that, and here is an example from Lower Austria, and we can also detect those quite well with our time series. This is an example. Here you can see with the aerial images, because most people are not so familiar with the Sentinel data to have a look at, but this is quite clear that here are the trees are dead or already recolored, and this is the result which we get from the satellite time series analysis. Okay, so that was more or less what I wanted to show from time series point of view. I have now a few slides from our airborne data acquisition module, because what I just filled them in this morning because I thought it might be interesting for some of you. and I'll be very brief. It's just what we developed for areas where you need higher resolution data. So Sentinel data is 10-meter resolution. It might not be sufficient for all applications. And also, we have a laser scanner with that. So the problem is that many countries, these airborne remote sensing facilities are non-existing. So you don't have an airplane equipped with the sensors, which you want to use. And the transfer of such an airplane from a neighboring country might be very expensive. And so what we did was to develop this kind of box, which you can transfer on any normal aircraft. You can fly to Suriname, where we have already had a lot of projects, or to Brazil, or to Burkina Faso, or wherever, and then mount it on a wing strut of a Cessna 182, for example. And this is an airplane which is very often available. And then you can do that, install it in 2 hours, and then you're ready to go. What we have is optical camera and near-infrared camera. For those who don't know, near-infrared is important for the vitality of the vegetation. And we have also a LiDAR. A LiDAR is a system which allows to measure the distance. So you send out a signal, you measure the time until the signal gets back. And the nice thing is that it can go travel through the leaves, so you get an information on the ground as well. So you can measure tree heights, basically, or vegetation heights. And you can get very nice information on the ground as well. So that's for different applications like vegetation or planning or whatever. Okay, so I'm at the end now. So my take-home message is something like, there are large amounts of data available. Let's make use of it. Thank you.
Decide immediately. Decide immediately.